All right. Let me put this on Discord.
Yeah.
It's very nice that we now have a multi-GPU channel.
Oh yeah, and we're doing single GPU stuff.
I mean, you have to understand how to rotate the shapes. Was basically my like that was the conclusion of me talking with you last time. It's like basically it was cool if you know exactly how to rotate them, but if you're like, oh, like what would happen if I rotate it this way, like then it's rough.
I mean, I have issues about that as well with that.
I don't know, like I used to always think I'm like more of an algebraic guy, I guess. But then again, like I think once this stuff gets like this, it's just very hard to do anything algebraically. Like you kind of need to just try to map things in your head a bit. Anyway, I don't know how someone can. Yeah, I don't know how anyone maps this shit in their head though.
Yeah,
Anyways,
did.
Anyways, okay, welcome everyone. So for context, we're gonna be taking a look at this blog post called "Into the Matrix," like written by one of my former colleagues, like Basil Hosmer. And what's kind of really cool about this blog is that it gives you like these interesting ways of like visualizing matrix multiplication, and I think like this blog did go viral at some point. Like both like Matei and I think saw this thing like years ago. Yeah, like almost like 2 years ago. And basically my TLDR at the time was like, wow, like cool pictures, It was like, okay, like this is cool. You want to get it to whack your stuff, you get to shit like this, and you're like, okay, like, but after like revisiting this blog a couple of weeks back, like I realized that it's actually it's like a very helpful framing of like thinking about matmuls. And specifically, what even made me even more interested in this was that like when I was exploring D-tensor stuff with Matei last week, it was like very clear to me that like you kind of need to be thinking in terms of shape rotations. And what I mean by this is that like you have a tensor, like on which dimension is it sharded? Like what does it look like? If you take a tensor that's sharded with like in one specific way and a tensor that's sharded in a different way, like what does the resulting tensor look like? Like how does this look like for your experts versus like your input batch? And let's say a new paper comes out, like how would you go about like visualizing what it's trying to do? So suffice to say, like I think shape rotation is like a very good prerequisite for understanding D-tensors. And I'd say like just to be upfront, like neither Matei or I understand this blog very, very well. So we're gonna try our best. Like I've read it like 3 times now, and I still don't understand it. So maybe this 4th time will work out. And basically, if folks in chat have any questions, just like let us know. Otherwise, we'll be sort of going over every picture and convincing ourselves that we understand what it does. And if we have time, we'll try to sort of apply some of those ideas to some D-tensor program. And if we don't have enough time, we'll just probably do it like in yet another session.
Yeah, I hope there are going to be answers in chat, not questions, to be fair.
That's fair. I mean, if Basil's in chat, please help us out. All right. So the first thing like the first thing they mention in this blog is like typically when we're doing like matmuls, you can effectively picture like we effectively picture it as like this like 2D operation where you want like the inner dimension to match, and instead like Basil covers it in a fairly different way. So for instance, here at the very top, you can see like this is multiplying a matrix L times a matrix R, and then the result is L times R. The way to read this, and again, this took me a long time, so like, but basically this is L, right? So it's I equals 32 and 24. The inner dimension on which you're multiplying these two vectors, these two matrices, is this one. So basically it's K, and K is of size 24, which basically means that like if this is of size 24 here, you can sort of see that its output doesn't show up. And so like you basically end up with a matrix L times R that's like 32 times 32. The way to read these is that these are individual elements in the matrix. And these are basically blue. You can think of it like positive values, and red is negative values. And so let's try to picture this. Like again, this is not super well explained in the blog, but like let me just quickly show you here. So basically what this is doing is this like when we're doing a matrix multiplication, like typically we know that we're gonna, for the first matrix, we're gonna take like a row of it, and then we're gonna take a column of the J matrix. And you can kind of see this here. Like you basically, I guess, Mate, do you see it? Like this thing going down.
Yeah.
And then here, like how it's sort of like scanning like over the columns. And for every element, we're basically going to take the dot product. So for example, here, if we look at like these elements, these are all going to be like small ones. And then we multiply these by like other ones. And then, this like let's say positive, like a small positive and a small positive gives you like another positive value. But like as soon as you get to here, for instance, like let's say we're at this point, like basically as soon as the first blue goes through the red, let me restart this actually. As soon as the first blue goes through the first red, you notice how all the values like become red, and that's because we're doing like a positive times negative multiplication. And what's interesting here is basically the way we get these colors is this is just like an input distribution. Like basically, for example, this is like it takes every element, divides it by 8, and then like does a modulo 2 plus 1. And you basically end up with this like neat pattern, and then you get like this like checkerboard pattern in the output distribution. What's kind of cool about this is that like you can also fuse. No, it wasn't here. You can fuse. Where is it? Remember layouts? No. Logchain? No. Deco? No. Oh yeah, epilogue. So let's say we want to fuse like a ReLU. Like what the ReLU effectively does is it like removes all, it's just basically max of your current value and 0. So it's going to remove all the negative values, and we can basically see now like this is the impact that like having a ReLU would have. Whereas if we take something that's no, not sigmoid. Yeah. So for sigmoid here, instead of like completely zeroing out the values, we basically end up with these like very small, like small positive values. And overall, this is kind of cool, like not because like for like maybe this individual visualization, it works fine. But I think the thing that's kind of interesting about this blog is that they will eventually like expand this to much more complicated patterns, and then things like distributed programming and LoRa's and flash attention and what have you. And I think this is kind of where it gets interesting.
Yeah, right. I think we can understand this one a bit, but the next ones are kind of tricky.
All right. So this one, for example, is this one is cool. Like basically, this is like a matrix. So this is again like a matmul. But we're taking like every row of the call. So we're taking every row of the matrix L. So basically, we can think of like matrix multiplication as either taking all the individual rows of L and then multiplying over them. But we could also think of it like in the other way, which is like, yeah, this is where it gets like more galaxy brain, by the way, where you effectively just take the whole, you effectively take the whole matrix and then you project its values like inwards. I don't know if that's a good way to explain it.
You can think of this like, I guess, like when you have a one token with you can think of this like batch matrix multiplication kind of. Or like a batch vector matrix multiply, I would say.
Yeah, like a batch vector matrix multiply. Yes, I think that's correct. Yes.
Yeah, so I guess this is like kind of simple to understand and like understand what's happening. I mean, I can think of this like data parallel version of the last one,
Yeah, so here, like for example, they do the matrix vector prod, and then I guess the vector prod would be like the other way around. Oh, interesting. How is this? Wait, do you see this? Like the values are slowly increasing. You're seeing it too, right?
Yeah, I don't. Wait, I'm not picking up this one actually.
I think this feels to me like an accumulation. Like you're basically going over all of the columns of the L matrix, and you're accumulating values inside the output by like scanning over, by like doing like all these like dot products with the R matrix. So this is what you see, like, because it's.
Oh, I see.
Is this also true here? It is not true here. So here, this just fills in the value automatically. Oh, but maybe here you're accumulating the values within the inner projection itself. No, it just feels like it's switching. There's no
What
projection.
is the difference between those two actually? Like,
So I think this one is so there's like vector vector product, vector matrix product, matrix vector product. So vector matrix product is, I think, how we typically understand matmul, right? Like you basically like, so this is
it went downhill
oh,
basically.
I see, I see, I see, I see. Okay, so you basically the thing going down is the values of like the matmul over like a larger dimension, and then you basically sum up all the elements along like a certain column. Like basically, if you take the sum of all of these guys as they're going down, you basically end up with the value that's here in the cell, right?
Wait. So, like, over which dimension you take a sum?
So you're taking a
Over.
dimension, so you're reducing over the inner dimension, the k dimension is what you're reducing
Oh,
over,
yeah. Okay, makes sense.
right? Yeah, okay.
Yeah.
All right. All right, yeah, I forget that, like, okay, well, let's do what's AXPy? The fuck is this?
I
Okay,
think
so
that's
this
just. I mean, this feels like the classic. No, you just take but a classic where you accumulate.
yes, so this is how we would do, yeah, so this is how we would do matrix multiplications by hand, it feels like, right? Like
Yeah, I think
we would
what you
go
can
every
think of
element,
this
yeah.
is like when you do a kernel for block matrix multiplication, or like a matrix multiplication over blocks. Like tiled one. If you imagine, this is what you do basically. But here you don't have a tile, but you have a single element. So your tile is one by one.
Ah, I see, okay.
You
So,
just go over k, and you just go over k and accumulate. In classic tiled matrix multiplication, you go over blocks in k dimension. You know?
so what's sort of interesting here is that like all the different, like all these different functions, like basically, like whether it's the dot product, the xby, the vector matrix multiplication, the matrix vector, vector, all give you like the exact same output. It's just like a different way of thinking about like how do you go about doing the matmul, but like they would give you the exact same output. And I think like the most inherently parallelizable one feels like I think, yeah, the matrix vector and vector matrix. Those are just like the fastest operations, it seems. Right? And then one like moves it this way, the other moves it the other way.
Yeah, that's just a difference in them, right? Like a difference in order.
Okay, so here's something I didn't quite get. So here, for instance, like the values here are, remember, like the smaller the value, if it's a blue value, it's a small blue circle, means it's a small positive value. And big red means it's like a large negative value. And at some point, he goes, note the prominent vertical patterns in intermediate matrix vector products when we use randomly initialized arguments, reflecting the fact that each intermediate is a column-scaled replica of the left argument. So this one I didn't understand. So
okay, so let's intermediate matrix products. Intermediate matrix vector products.
I think for the intermediate that he means like this thing that's like mapping over the space, right?
Yeah.
And so yeah, I mean, so what does he mean by scaling? Does he just mean an element-wise dot product?
Well, wait. Come. Well, So I think what they mean by that is like that each
The matrix vector product, yeah. So we're multiplying this matrix by this vector.
Yeah.
Oh, and I wish we could pause this. You can't pause it, unfortunately.
Just take a screenshot.
Damn. Okay. Okay. So, okay, I see. So you notice here the thing that's highlighted at the top, like mostly has a lot of like blues, like large blues.
Yeah, roughly, yes.
Which means that I would expect, like if I'm multiplying by a lot of blues, the blues will stay blue, and the reds will become red. Well, actually, no. Yeah, that doesn't make sense. Would it just be an identity?
Yeah,
It
like
wouldn't.
wait. So you have like a bull red. So you have a lot of bulls. So let's say that in top you would have only bulls. That would mean you have 50-50 distribution. Like it would just depend on the distribution of the core, right? So, but we don't have only bulls. We have also some rats. How am I supposed to think of this?
Let me think. Oh, so one fairly obvious thing from this picture, maybe it's not the blues and the reds, but notice how everything just looks smaller there. Like basically, you notice how here, like the big guys, there's only like a few, but here there's a lot of big guys. So basically, this like scaled down most of the values that we have, right? And I think we can see a lot of small blues. So we're multiplying by, oh, so this is what he means, right? Okay, okay, I think I get it. So basically, you have like large random values here, and you have small random values here.
I mean,
which means
pretty large to me as well, by the way.
No, they're like
the top
yeah,
ones seem pretty large to me.
Wait. Let's take a look at the thing again. It's not. Look.
They're the same. You can't convince me otherwise. They're the same. Like,
I'm reading tea leaves. Okay, we can confirm by looking at the input distribution. So this is the Gaussian.
Okay.
And this is the Gaussian as well. You're right. They are the exact same. I think I was reading tea leaves. I'm seeing patterns in the skies.
Okay, I think it's gonna be the colors. Like you have, but no, that. Wait, you can change that. It's insane. Wait,
yeah,
wait. Now, look at it. Look at it. Just no, the other direction. If you go, it basically stays as a copy. Or I can invert it, I guess.
So no, it's not like for copy you can get it. It's basically here if you do like a
no, but if you do it like the intermediate is just a copy, you know, when you go back to the visualization that you had before. But with the distribution that you had, where like the top was half red, half blue, you can see that the intermediate is just a copy of the left matrix, of the L matrix. Or like left side of the matrix is inverted and right side is the same because you're multiplying by 1, basically.
You're right. Like I see it like on the right side, it almost matches exactly, right? Like let me.
On the right side, it's exactly matching. Like,
yeah, let's do this for example here.
Yeah. So what that means, I think, is that like you basically just scale the distribution in the left matrix in the L by the distribution in your top matrix. That's the intermediate, right?
Yeah, so every column is effectively a scaling factor.
Yes.
Yeah, I see. Okay. Okay, I think that makes sense. Let's see, vector matrix products. Oh yeah, this one I thought was kind of cool. This is if you do the identity. So like in this case, they do 24 times 24 and then 24, 32.
Yeah, that's kind of reasonable.
Let's convince ourselves that this makes sense though. So he's going down, I think, first off, he's doing the vector matrix product. What happens if you do matrix vector product? It also works, right?
Yeah.
Yeah, I mean, they all always work, I guess, but let's build intuition. Okay, so for example, here it has no impact as it's like positive times negative gives you negative. And we would expect this to only change once we get here.
Yeah, that's. I think a good way to think of this is like what you do each step.
Yeah, I mean, like I think personally, I'm finding it easier to think of dot product because I can map it to like how I would do matmuls by hand. But I feel like we're kind of missing some of the magic by relying on that as opposed to like, I think like maybe the intuition with the other ones feels more. Oh, what's going on here?
What? Wait. This feels kind of. Oh, okay. So they make a vector out of like the diagonal, and then they just do. Is it a vector? Wait.
Oh, so they multiply. Okay, okay, wait. Let's do the. Man, we should ask them to for a pause. I'm gonna do this. Yeah. To the here. Is there a pause function?
Professional complainer.
100%, yes. I mean, I feel like it's Claude should be able to vibe code the pause function.
Could we get
Let's
the vibe coded pause function?
let me just do it in the background and we can get back to it. So cd
Just throw a bunch of agents at it. Let me grab a water actually. Well,
take your time.
wait, so what's happening in this one? I'm kind of lost now.
Okay, yeah, this one is kind of cool. Like basically, fundamentally what's happening is that you're taking like every point like still from the row and multiplying it by every point in the column. But in this case, like you only have like a single point. And so when you
Yes.
take the sum over all of the points, like assume they all just like are like no ops, like zeros. And so
Yeah.
you just basically get the individual value, which means that like you basically like map it back out. And then if you do it this way, no, not this way, sorry. Like this way, for instance, would be sorry, I think like this maybe.
You take a full row of R of sorts, I guess, row, and multiply it just by
the vector
by the
product is
column.
harder to visualize though. I feel like these are easier because like you want it to map like into the dimension that you're like about to read in. And I feel like this is the only one where it's like the arrow isn't pointing into the thing, right?
I never understand which one is vector, which one is matrix. I just have like a intuition into that.
All right. This is still okay. It's a chunky repo actually. How big is this thing? Oh, okay.
I
I
think
doubt anything is
assets is
getting
gonna
merged
be
though.
Yeah, I think assets is gonna be the biggest one though.
Ball. What is a ball here?
It's a ball.
Why do we keep running away from web development, Mate? It feels important.
Yeah, but I mean, if Code manages that, like you have this proven, you know.
If
If
I guess
what is it even
if
written in? Is
I
it
think it
raw
looks like raw
JavaScript actually?
JavaScript, which I totally understand. Like I would never
Yeah,
use.
3JS actually, 3JS and JavaScript like raw.
All right, let's not get nurse sniped.
Yeah,
So let's
I
go
think
back
we're just
here.
running from the.
Running away, 100%. Yes. All right. So what's going on here? The third planar decomposition is along the k-axis. Computing the matmul results in a pointwise summation of vector order products. Okay, so this is like the intuition we had, which is like you basically. Oh, I see. Yeah. So basically, you take the sum of every element, and then you sum over all of the points along the k dimension, and then you slowly build up the result this way.
Yeah, so it's just like tiled matmul basically.
No, this is more like diffusion. You know, like you sort of like are like you basically have a for loop that eventually gives you the correct output.
No, but yeah, like how would you do this? Like you have two outer loops over L or whatever the dimensions here are.
No, yeah, but my point is even after a single iteration, you have an approximation of the final matrix in this way.
Yeah, but because of the input distribution only.
Because of the input distribution only.
Yeah, because
fair.
if you
So
change it
if
to random, it would just blick kind of.
let's try it. Gosh, man.
Both of them have to be random. Now you're just scaling them. You see, they start they blink at the beginning. They switch colors because you're just accumulating, and then they just kind of go out of the go out from the zero.
But very few of them are changing colors. It feels like they're mostly changing sizes.
Yeah, I guess because you just start accumulating, but you don't have an approximation. Like how you can think of this, like, or how I think of this is just like a classic tiled matmul. You know, you have a have you written a tiled matmul in Triton, for example?
Sure, yeah.
Or like, yeah. So you do like the inner for loop over k dimension. So this is what you're doing.
I see.
You're doing the same, but your block here is 1 by 1, basically.
I see. I see exactly what you mean. I guess there isn't like a natural way to, but like that's a clever point actually, in that like we could visualize the. Interesting. I see.
So because at like if you were able to pause it at step 0, you would just do like element-wise multiplication.
I guess what's kind of cool about this is that like it also doesn't matter in what order you're doing it.
Yeah.
Right? Like the. Interesting. I guess like is there a concept of swizzling here? Oh yeah. Claude.
We don't have the extension.
Please. Make the enter function. Pause the picture. The spacebar. Okay. Okay, this one I don't think is anything crazy going on, but basically what he's trying to show you is that like there's this arrow, and if you have like A times B, the arrow is basically going to point towards where the result is. And so for instance here you do A, because this is A times B times C. So when you're doing A times B, you basically end up with this guy of dimension 64 and 96.
No, yeah.
Right? And then when you're multiplying it again by C, yeah, like it would be, where else would they put it, right? Like I'm trying to think about, is there any other way of visualizing this? Like if you put it, I guess you could put the C here. You could also put it here. Or you could put it, well, it depends on, yeah, actually you could put C here.
Yeah, on the bottom and on the top, I think.
On the bottom and on the top. And why did it choose to put it on the top? Because if you put it on the bottom,
Would it
then
actually? No, it wouldn't even change the result, would it?
I don't think it should. No, like I'm just trying to see like from a visualization perspective, like why make one choice versus the other, or if it's just like a.
Wait. So how would you do that? It's just you're doing a yeah. It wouldn't change the result because like if you think of this, like first column of A times B is multiplied by first row of. Can we speed this one up?
By the way, one thing I find interesting about this is that you see like there's still not a single element of A times B times C being computed yet.
I think it's because you can't. Like, well, you can start, but you can't finish because you're doing like a column of A times row of C, you know? And you don't have a column of A yet, of A times B.
Interesting. So this, okay, so this kind of explains why like you might need to change the memory layout then. So like, let's say we made, let me think about the right way to do this. So you're right, we need the whole column. So
yeah, if we were computing A times B column wise, like column first, then we could start computing C or like A times B times C already at the start.
oh, we just need, okay, so it's not about this init thing. We just need to change the, actually, let me.
I don't think you can change it here, to be fair.
I think you can, I think you can. I think it's basically you change the animation. Oh yeah, sorry, the vector product, right? The fuck?
No, this not this one. I don't think he actually implemented the like simultaneous. You have to.
Oh wait a minute, this is like another video game I made instead. Oh, okay, that's not what I wanted to do. Yeah, man.
Also, do you know that you'll have to like run this afterwards, which isn't that easy with JS?
Hopefully he has some instructions on running this. Let's take a look. He does not.
So you can just hope that npm build will or npm run, npm dev or whatever will work.
Right. Yeah, but I think like this is also helping me like a bit understand like if you could do things where you fill in the column first, like this also means that like you can start the next computation. It also like if this gets into sharding stuff, it's making me think about like how do you know which like a minute that a minimal chunk of the data is ready for you to start like overlapping compute. This is kind of like, but I feel like there should be a way to do this, but
Yeah, I think you have to go like along the rows of B, kind of like. How do you compute one point actually? One point is a row by row. Oh, right, but you ruin your memory coalescing so bad, or like you ruin your memory usage so bad by. Well, I
Unless,
see.
unless the tensor is column stored by default, it's fine.
No, not coalescing. That's not what I meant. Like you see, right now you're reusing your row of A for the whole column of B. You see?
Uh-huh.
No.
Oh, but they have, he has a step function, I think. So sorry, you were saying? Oh,
Okay.
wait.
So this, yeah, that one was the correct one.
Async, right?
Was that async? I don't see the letters on the right, so like I just see the pictures. You know, I like looking at the pictures.
Yeah, it's the sync thing.
Yeah, exactly.
Let me just slow this down because this is okay. So what's going on here?
Yes.
So
with this one, it's the same. Like you're just doing a row of A times column of B. It's the same as before, but the difference is in like what's your what's your fastest growing dimension, you know? Like in the first example, you took one row of A and multiplied it like one by one with each column of B. This time you take one column of B and multiply it one by one with each row of A. It's just the difference in like which is your faster growing dimension and which is your slower one. You see?
yeah, you're right. This doesn't matter, right? Yeah, so for the dot product, we can't get this. For xpi, we can't. So yeah, so we need async and we need VM matrix vector or matrix vector, presumably. Oh, matrix vector also doesn't work.
Yeah, it works. It just doesn't compute. Oh
no, I mean it works, but it doesn't start filling in it doesn't start streaming the results back to the final output.
Yeah, but it could, like, you could implement that. I mean, could you? Wait. So.
Okay.
Wait,
so
actually,
it seems like
it seems like
it seems like the winner is the vector matrix product. Like.
Yeah, I was actually wrong the whole time. Like.
About?
What was I? I don't know. I don't know.
Yeah, it's like
it's cooked.
Okay, so
yeah, well, you just need a full row of 8. Do you need full row or full column? Wait, I can't see it. Which is the dimension that you're multiplying on? Like
so
the A times B.
A times V.
Okay, so you need a full row of A times B to start getting the row with C, you know, because like you're doing row of A times B times row of C. It's
no. So sorry, like to get a row of A times B.
Yeah.
A whole row.
Yeah.
Because once we get a whole row of A times B, then we get the row of A times B and the column of C, which we already have, means we can start A times B times C, right?
Yeah.
And so the fastest way to get a row of this thing is we take all of A and multiply it by what exactly? We're not multiplying by a single column here. We're multiplying by the entire.
No. You take a row of A and you multiply it by whole B. Like you do a vector matrix product of
vector matrix product, yeah. So a row of A times all of B.
Yes, exactly.
Okay.
And you get a row of A times B.
So what's the dimension of that? So basically a row of A basically means it's of dimension 132.
Yeah.
Right? Times 3296.
By 96. Yes.
And so we're basically filling in like 96 elements at a time.
Yeah.
Oh, and so like I see your earlier point. Like you also need to think about like what are you more likely to fill up first? Like basically, is it like 96 rows or no, this doesn't matter for this one specifically.
Yeah, for this one it doesn't. But like what I meant before is like as the first inefficient implementation, you only had to load into memory like the whole A, which is a lot smaller than whole B. You know what the fuck? You're gonna get demonetized from the YouTube. I hope no one watches you, by the way.
100%. Okay. 32. Okay, let's say we're like this.
This is what is this one? Wait.
So the idea here is it's the exact same thing, but I flipped the sizes of A and B where I made the inner dimension huge. The inner dimension is now 96, and then the outer dimensions are 32 and 32. And my question was like, do I still expect the vector matrix multiplication to be the fastest way of doing this?
Yes.
Or will it be something else? And so here basically, so here you're basically filling in 32 elements at a time. Yeah, but that's my question. You're filling in 32 elements at a time, but you're having to do this 32 times. Oh, so it's still like you're filling in things 32 times, regardless of what we picked.
Yeah, you go over like the outer dimension. The thing is, like, this might not be like, for example, for this, or like the example before I had a better one. Like for this case, you need to. For this case, it won't matter because both the matrices are the same. But for the one before, you had to like discuss. So the fast way would mean that you need to have like a very big matrix stored in memory, or like near each other in memory, coalesced in memory.
Are you talking about a tensor? Or are you talking about like a specific like chunk of that tensor?
Do you have the old example stored?
Yeah, I can just reload it.
Okay, so if you do like the first one, which was the inefficient one, the one that can't overlap because you're doing column by column, you know? Yeah,
the matrix vector product, yeah.
You see that you're doing like the multiplication with a full matrix A, which is 64 by 32. Which is okay.
Yes.
If it's 64 by 32. But imagine if you were doing it the other way with B, the matrix that you had to keep in memory would be 96 by 32, which is larger. So in this case, it doesn't matter, but imagine it was so large that you couldn't fit it. Like you would need to, you know, like your GPU memory, like it would just go out of it. Like you couldn't fit it.
Couldn't you just transpose twice to avoid this and basically always make sure you're summing up over the? I guess this is why we have both column major and sorry, like major.
I suppose so. I suppose like and also I suppose like it's always worth to do this anyway because like you can start like asynchronously computing C in the end, which with columns you can't. Right? Yeah, so with this, even though like you need to store a smaller matrix in memory, or like compute with a smaller matrix, you can't start computing the final matrix multiplication.
Yeah. So you'll get better cache behavior for like a slower for a blocking synchronous algorithm. And you just have to basically do the benchmark and see. And then and then for vector matrix multiplication. Oh wait, why is this not working? Oh, because I don't have sync. Sync.
Yeah, you get a worse like cache usage because you need to have more things. Or like I guess the worst case could be that you need 2 waves on GPU to compute this like you know, like the B is so large that you don't fit into 1 wave, so it takes like twice as long because you have like a half wave running across the GPU, you know?
Mm-hmm.
But I guess it's still worth because you can start computing in most cases. I don't know, like I guess you need to benchmark this, but like that's just my understanding of this.
Yeah, my sense is this is like going to be very shape dependent. Is
Yeah,
I guess like my high level guess. But I guess even if we were to like, let's say just like naively, we're timing this algorithm. Like let's count this out. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Versus 1, 2, 3. This must have 4, 5, 6, 7,
yeah,
8,
of course.
9, 10, 11. Yeah, okay. I guess it doesn't matter though, because like well, no, this does matter because like even
I
if
mean,
GPUs are
here,
parallel, like
if you think of this, like here you have 96 plus 32 steps basically, and then the one before, like if you go to the, you see, because you go over J dimension, which is 96, and then across the second J dimension, which is again 96, and here you only have 64 steps to take.
interesting, yeah. So
I mean, of course, GPUs are a parallel processor, so it won't be like.
no, but the GPUs are parallel processors, but which also means that like they don't like data dependencies, and here there is a data dependency.
Yeah, of course.
Okay, very nice. Okay, we understood something.
Yeah, at least.
I think. Okay, what's going on here? So this is A times B times C. So A times B, where's B? Huh?
On top. You're doing A times B times C, but you're right associative, so you're doing like right to left.
I see. So B times C, you get B times C, and then you put A, and you get A. Okay, got it. That's cool. Binary expression.
What is this?
So more parentheses. Although I find this wild. Like, I mean, can you convince yourself why this would produce a checkerboard pattern? Like, I'm not sure I can, to be honest.
Okay, let's do like 2 minutes of thinking, and then we might.
All right, yeah, do some like shape rotation.
Don't do shape rotation. I have to watch. Okay, wait. I'm gonna take a screenshot.
Let me do the animation. Okay, I don't think this specific animation helps though.
I'm not. I just need to watch the picture. Look at the picture. Okay, I got it. Actually, it's kind of simple, I think. Or is it? Wait. Across which dimension am I going? So it's this times this. So it's this times this. Okay. Yeah, actually, it's pretty simple.
All right, tell me.
So if you think of like the two, like D times C, for example, or C times D, you're doing across a K dimension. And well, you're doing across a K dimension. So you're going like a half red, half blue with identity or inversion. So you get like inverted.
You're right. This literally inverts the colors of this, right? Because
Yeah.
it's like, okay. And then this.
Well, it inverts half of it. It inverts half of the colors of it.
Oh yeah, you're right. It's not like a clean inversion. It's like a flipped, right? It's not like blue became red.
Yeah, because it's kind of tricky because of how the dimensions are aligned. Like it's 64 by 64, but all of them are 64. You go like column of C times column of B or column of D. Like you don't go row by column, you go column by column. You see what I mean?
Why are we going column by column? No, I don't see it.
Because contracting dimension is K, which is columns in both.
Oh, like I see.
It's just an annoying like coincidence or whatever that all of them are 64, but you're going column times column. So like the column of C basically inverts half of column of D. So that's why you get like the half pattern. Then like it tells you that like this the column of D that are interchanging, so they tell you like the pattern of C times D is also going to be interchanging. And the same ish thing is going to happen for A times B. Again, you're doing row by row this time because, again, that's the contracting dimension. And it's the same thing happening all over again. Like you have identity and A inversion.
Let me do this. So like here, for example, if you go over the row, it's about like half of the matrix. And so red times red, so negative negative will give you positive, negative times negative times positive will give you negative, positive, and then negative.
Negative. Yeah.
Yeah, and then positive. Okay. Oh, I see. So this explains. Okay, so this one I get. This one is easy. I get it.
Yeah.
Let me go
this
back
one also,
here.
I mean, this one, like, I don't know if it's correct, but like you can see the scaling of it, kind of.
The scaling of it.
Like the scaling, that was the example that you were reading the TDs. Like you're basically scaling one matrix by another one, or scaling a column of one by another.
You're scaling a column of one by another. Yes. Man, we really need this pause button. Cloud gave up, I think. It's like reading other repos. Okay, Cloud, go away. Sorry. You can't shape rotate. So let's just do the basic convention. So basically, this is all blue, and then it's going to go over
half red, half blue.
Half red, half blue. Which, oh, I see. It's basically if it's horizontally, like basically if you get like red rows and then blue rows, this will manifest as red columns, blue columns. If you have in your specific row an A, it's the same color.
Yeah.
Okay, I see. Okay. Partitioning and parallelism. Okay, see, now we're in your territory. So I think this one is, yeah, like A times B times C times D times E.
Why would we do that?
And A is 64 divided by 8 in dimension. So how do you do this actually? Left A, where's A?
I don't see that at all. So like it's on you.
I see. A times B times C, D, A times B, left A expression. How do you do data? Oh, interesting. Yeah. So there's an argument called blocking. So for example, if I put blocks along the I-axis, I basically end up with this. So I guess, yeah, if you have like A is sharded per row, so like this is
data parallelism.
This is the data parallelism. And then A times B will also be data parallelism. Pretty much it's infectious, like almost everything after remains at this ratio of, so here it's 6. Let me make it 8, just as it's easier number. And pretty much everything stays till 8 till the very end. Now let's say we also introduce model parallelism.
Yeah, because like this example is actually very simple. Like this one is the one before, like just the data parallelism. You can think of it like three linear wires happening basically, because like you get it like your basically A times B is going to become your Y, then you multiply it by another weight, which is C. That's going to be like your Y2, and so on and so forth. That's why this is like group gem, I guess. Well, not entirely, because you have the same weight matrix, but you know what I mean. Yeah, okay, that was a bad example.
I'm still failing to understand. Like, I totally get the I blocks, but like, let's say we just make it 1 again, and then we go to the K blocks, and I make it 2. What am I looking at now? So if the
Okay.
K blocks is 2, why is it not split here?
I suppose it just split the last one, like because like your A is. So think of it this way. So A is your data, or that's how I would think of this. A is your data, A times B is your activation, A times B times C is your activation, A times B times C times D is your activation, and so forth. So, like, matrices B, C, D, E are your weight matrices, right?
Wait, let me just double check one quick thing. So here they're saying the right. Oh, only E is in the right. Everything else is in the left. What does that mean? It's a matmul, it's a matmul, row major, column major, speed. Okay, never mind. Okay, does JBlock do anything? I think it does the output, if I'm not mistaken. Yeah, it does the. So J is easier because it's actually just the like there's no other J's and oh no, there is a bunch of J's in the program. There's a J here and there's a
I
J
think
here.
it just does it for one. Like, I suppose that's just the
I
limitation of the
I
program.
think it's just different J's because this is a J32
Yeah.
and then this is a J96.
Oh, I see actually what would. Yeah. So if you did like K split across B.
K split across
So
B.
you would have to do like a. It would. Can you do that actually? Can you do K blocks on B?
Yeah, actually, you can put blocks on. I think we were just putting blocks on E. So here's what I'm
Yeah.
gonna do. I'm gonna go to, like, let's say we're gonna do something wacky where I'm just gonna take A and actually for A, I can't seem to shard it though. Actually, no, wait. So
Well,
A,
you were
let,
doing.
let me make the viz easier for you. Can you see now?
It's the same. You can just do full screen as before. It was fine.
Okay.
Like,
Where is the animation block? Oh yeah, so let's say we blocking C.
it's C block. Wait, what is that? Or it's A block. Like, it's blocking A. Yeah, it's blocking A. No.
Okay, and then this is blocking B though.
Yeah, that's fine because then you have to block C as well. Actually.
Oh no. Okay, here's how this works. Let's say you have C, right? Like let's
Yeah.
say let's call this C, right?
Let's call it Y.
Y. If
We
you call
already
it
have
Y,
C.
yeah. If you call it Y, if you block I, K, and J, it means you're blocking both the inputs and the out, and then J would be blocking the output. This is what this means. So like for every one of those, they will have their own like they will have 3 blocking numbers if they are intermediate values, but you don't block an input, you block an output. Like basically only this can be blocked, and then once you like if you choose to block I and J for this, you'll block this. For example, let's say here we're at A times B. If I increase this I block, I would expect to increase the data parallelism of A, which is correct.
Yeah.
And if I change K, I would expect to block
No,
B.
K is not there. It's J. It's J all the way.
K.
No, K is your contracting dimension. Like A times
Yeah, and
B,
then
K is your
J,
contract.
and then J would be the output itself. So basically,
All right.
oh
How
no,
can
no,
you?
no, 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 no. All 3 of them are inputs. Actually, you're right. Like it's
Yeah.
basically the so K is the contracting dimension, and I and J are the outer ones. I see. Oh, I see. I see.
So if I think of this like I times J, so if you increase I, you just get, or like increase blocking for I, you just get data parallelism. That's simple.
Mhm.
If you split on K, that is sequence parallelism. And if you split on J, that is model parallelism.
So what's interesting about increasing K is it has no impact on increasing, on changing A times B.
Yes.
You notice this? So changing the inner dimension. Okay, I think someone's pinging us in chat. Full visualization. Okay, never mind. Okay, this is cool. Okay, so changing K does nothing, which I think lends itself to why. But why do you say this is sequence parallelism though? Like, why isn't this just like model parallelism?
Wait, it's not sequence parallelism. Sorry, this is model parallelism actually.
Yeah,
The other way.
so model parallelism here in this case would be like you have like all of these shards basically on different GPUs, and you're effectively, let's say on rank 0, bringing the two respective shards that you need, doing a local computation, and then like going on to the next like 2 shards that you need. And does this actually work? Yes, because let's do the animation
Actually,
now.
no. Actually, I told you wrong. I think this is not even like, because this way, like imagine B are your weights. So you shard across the contracting dimension. So you do a shard of 0, which is a shard of 0, which is row wise. Yeah, okay. This, you can't think of this like model slash row wise slash call wise parallelism. I think it just won't work.
So what is going on here? Like, let's say we took B and we split it into 8 chunks. And
Yes.
now when we're doing a matmul, let me go back to animation and I'm gonna do, let's say the vector matrix product. Wait, why is it? Oh, it's slow. That's
You
why.
probably wait. Yes. How does this even work? Wait. Because you're chunking the contracting dimension. So how can you?
It's never coming back here. It almost feels like this is pre-computed or something. Something weird's going on.
I don't think you can even compute this.
Ah, I see. Wait. I think the animation should come sooner. Huh? So I want to get the animation for A times B times C.
Yeah, I just want the one for A times
So
B, and I don't.
for D. For D, right?
Can you do A times B? Like, can you try to figure out A times B? Because I don't think that's even possible.
Yeah, so this is A times B. And animation here only says inherit. So, but if I do matrix multiplication, it doesn't do anything.
Yeah, because look at, so my idea behind this is, oh, I see why you can't do it, because you would need to introduce communication for this. Look, if you go back to the, okay, I get it now. Can you go back to the previous slide?
Previous slide.
Or previous, not wait, the one where it was sharded across K.
Yeah, let me figure it out 1 second. It was E, and then blocking. So instead of blocking across E, we're gonna block across. No, so here. No, it's not before. Okay, this is on C. I think we're doing A times B. Yeah, this one. Okay, great. You're here.
Okay, so why this can't like do it for you? Because this actually introduces communication. So if you want to compute a single element, like let's say the top left element in A times B, that one, you would do that as a first row of A.
Yeah, and a column of B. But
yeah, those are sharded, so you have to do like the communication between them.
Okay, so and then for just to get this one element though, you need to get all the B's.
All the B's and all the A's.
No, not for the elements. You're fine with the elements. Or like if you just want to compute this one?
No. You need all of them, because like you're doing a full row of A dot full row of B, like a dot product.
I see, I see, I see.
So that's why this one can't compute it for you, or like the visualization for it, I think.
Okay, so let's do the last one, the J blocks. So J blocks is splitting across the output dimension. And if you split across the output dimension, you would expect your output to also be sharded.
Yeah, this is a column-wise parallelism.
Column-wise, what's column-wise parallel? What do you mean?
Column-wise tensor parallel. The
Oh,
one
I
we
see, I see, I see.
implemented.
Yeah, yeah, yeah,
You
yeah,
see
I
it
see, I
here.
see, I see. Yeah, yeah, yeah. Oh, I see. And so then if we wanted to do a column-wise times a row-wise,
Yeah,
how would
this
that
it
work?
actually did. It actually did
Oh,
row-wise for you.
I did column-wise, and this is like row-wise.
Yeah.
And then you can materialize a full tensor back on this side.
Yeah. Well, you would have to do all reduce on at the end, but like.
Yeah, so here basically every row of A times B would need the entire column of C, and so then you're reducing. I see. So you need to all reduce everything.
Yeah, so what you can do is like you can if you turn it, like you can do the first row of a block of B, or like Y, let's go A times B. No,
Yeah.
the other direction, like this way. Yeah. So
Mhm.
like you can do a first block times first block, then the second
Yes.
block times second block, third block times third block, and then you just all reduce all these together and you get a correct output. So that's
Yeah, I see, I see. Just okay, I see. So like here, and in this case, you're basically you're basically doing a reduction across the K dimension.
yes.
Interesting. Okay. Okay. I'm optimistic actually, Matej. We're doing this.
We're cooking.
So
Now
this is,
attention heads are coming up.
no, I think this is more chill actually. I think it looks crazy, but I don't think it's that crazy. Okay, let's take a look. First off, the formula. So out is equals to attention, where attention, oh no, so attention is equal to, okay, wait, this is like a weird, okay, I'm just gonna read it from inside to outside. So V is input times WV, K is W times input T, and then Q is input times WQ. And all of these are multiplied by W out. Oh, sorry, this is attention, and then you multiply this whole thing by W out, and then you get out. And so basically, okay, so then what the fuck, like these, so this is like the actual GPT-2 head, by the way, presumably.
Really? That's actually quite cool.
This is like the mask here, I guess.
Yeah.
Okay.
So
okay, so basically, okay, I see. So the input, let's say it's like 256 times 768. 768 is the inner dimension. 256 is the batch. WQ is something small on its output dimension, but something large on its inner dimension. And when you multiply this out, you get Q.
But this is just for one head, by the way.
Yeah.
This is just for one head. So that's why Q is small. Like Q would be way larger.
And then is there something interesting in this pattern, you think? Anything you see in the colors?
Are we going to read some tea leaves again? I mean,
Maybe.
they look very calm-like to me.
That's a good point, actually. And then, okay, then.
But I think again, this is the scaling that we were discussing. Like it just scales the column by.
Let's look at the clock tea leaves.
Right there, actually, we can take a look at it and understand like what the dimension is. By the way,
The model may have learned to apply consistently specific tokens regardless of content.
okay, can you go back to it, like, just so I can check it a bit more, like? So, what dimension is your column? Column is that's like a sequence length, right?
So column in this case is
Yeah, sequence.
256. Yeah.
So batch or sequence.
So this means that, like, I mean, what Claude is claiming is that this means you're paying attention to position disproportionately more. Why is that the case?
No,
Because, yeah.
I don't think it's the case, but like, I think what you can see back there, it's like, again, this is a very. I don't think this actually.
So for example, this is interesting. So this is, to me, it seems almost like saying, actually, maybe we should ask a more primitive question. So in Q matrix in attention computation, what does a column represent? Right, I think this is, it represents the query vector for a specific token position. So each column contains a d-dimensional query vector, and the column index corresponds to a specific position in the input sequence. Also, it's not reading tea leaves. So this means that, like, there's certain, maybe it's a head that pays attention to syntactic information like capitalization and like dots and things. And so this is specifically layer head, layer 5, head 4 of the GP2's too small configuration.
Okay, let's go back to the visualization.
This is not, yeah, this is not helping, sorry.
Yeah, it's fine.
Okay, so let's get back to the pattern. But okay, I think after that, all the other ones are kind of similar. So basically, this is also like input 256 and the K is 768. So yeah, so you basically end up with here you have your QKV, and then attention in this case is.
Can you actually show, like, what I'm interested in is like Q and K, like what's the, because you're doing just show like the output of K, like the big the K times VK, you know, like the pattern of that.
K times,
because like you're gonna be multiple, like grow of attention is Q times K, right?
Q times K. Yeah, I mean, this is a Q times K. It's basically this.
Yeah. So like I'm wondering, like, what's the, can you take a look at the K matrix that is going into the multiplication? This one, yes.
Yeah, the rows are much more striking here, right?
Yeah, I mean, that's the same. Like, you're just gonna do a multiplication, like element-wise multiplication in the attention. Like, you're gonna do q times k transposed, or q times k, or what?
No,
Yeah, q times k.
I understand, but like the interesting pattern is that like if you view it like a lookup table here, the K is saying there are certain important rows, and then the Q is saying there are certain important columns. Which I think if we look at maybe some J. Lamar blog, he might be making some claim like this.
Wait.
It's fairly striking. Like I don't think these patterns are like again, like you see, like all the dark colors are rows. Like it's basically here near the beginning, like, and then near the end, and then it's just like empty everywhere else. Like,
yeah, but like the shorter dimension represents your sequence line. So I would assume that like your key, this tells like the matrix that you should be looking more. Wait, no, that's yeah, it's a sequence link, right? Yes. So you can see that the first 3 or 4 rows are quite large.
so look, I mean, let's go back
okay,
here, right?
I actually see it. So
Right.
what you can see is like in here, the first 3 columns or so are fairly large in negative values, or like you see like the big red column.
Sure, yeah.
And that one is gonna get multiplied by a second column in the queue, which is like really green. You see it?
That's correct. So we're gonna get like very large negative values.
Yeah.
Which means 0. So this is just the attention. This is just the masking then? Like, is this? No.
Wait, I don't. No, I'm dumb. But we're multiplying wrong things with the wrong things. Oh, the contracting dimension is the short one. Like we're gonna be multiplying a column by column, or you know what I mean.
A column by.
So like this short
No,
dimension.
I mean it's still a row times column, but I see what you mean. Like we're just multiplying over the
anti-pattern, I guess. Like
the J dimension, yeah.
Yeah. Okay, so let me rethink that. Like, what's this gonna result in?
So here you mostly have a bunch of small values. And so you're gonna get something that looks close to 0. Actually, maybe let's do that. Do you want to do the animation?
Yeah, sure. We're looking at wrong patterns, by the way. Like,
the fuck is going on here? Okay, my browser is lagging a bit, by the way.
The output, I suppose, is already doing softmax, right? On top of it.
I don't think they I don't think they added a softmax here now, but you can add it here with the epilogue, like a softmax. In which case, like in this output, why are we only getting positive things now, though?
Because of softmax.
But even without softmax, I think it's almost positive. Yeah.
No, it wasn't.
Oh, it wasn't. Yeah, I see. Okay, let's read the tea leaves a bit. I'm seeing like a B pattern or something. What do you think? Do you see
now
the
we're doing convolutions.
What do you think?
It all boils down to convolutions.
I mean, what isn't convolution, right?
Yeah, exactly. Okay, I mean, I'm not interested about this. This like out is not interesting to me. Like the interesting part to me is the Q times K. You know, the attention mask that we're computing, and like, why is it like this?
Yeah, I see your point. Like attention times V is also actually. Let's take a quick look at this one. Any interesting? Because you'd expect this thing to have a very peculiar structure after going through the mask, but I don't see it. It seems to look very normal
Yeah,
to me.
because it's not going through a mask. It didn't soft mask the mask. This one, you can see that you're just paying attention to like the closest tokens to your particular token. Like token 0, if you soft max it, it's gonna become a bit more green, like a bit more stable, I guess, the attention.
There's a lot of red here though, like there's dark red. It's not like a...
No, but like the output, look at the output of the attention, like the attention matrix. So you can see that this is very like...
Are we talking about attention times V?
No, just attention, like the big one, the Athena 8.
Yeah, okay, yeah, sure.
So you can see it's like very spiky towards like... So what this means, this is like...
Sure. This is like there's like a strong neighborhood attention kind of like aspect here, like because like these are like everything else mostly 0.
Yeah, if you normalize it with softmax, can you put an epilogue in softmax?
But the epilogue will only apply to the whole thing. Do you want me to just delete most of the stuff, like W0 and stuff?
Oh no, I've ignored that. Wait.
I think I will.
Wait, but you do no, but oh right. I would like to see like.
Okay, Matei, look, it's faster. It's faster. Chill.
Okay.
It actually runs now. The fuck is this? Yeah, it actually runs at a decent speed now.
Okay, so the thing I'd like to see is like attention map.
Yeah, so why is this like just only blues, for example, already? Like that also seems strange to me. Because I don't think there's a... Actually, wait. So this should show up. We have left. Okay, left. Oh, attention, yes. There's a matmul, and then
wait, yeah, I think it's like
it has that epilogue. Yeah, it has that. It has that epilogue. Look, because if you don't put the epilogue, it looks like this.
Okay.
So yeah, it just wasn't clear that there was a softmax there. This looks kind of cool, you know.
But epilogue is actually mask plus softmax. It's not only softmax.
Epilogue is mask plus softmax. Yeah, correct. Because, like I think, yeah. It's basically, well, actually, it was this. It's basically a softmax. I think it was this one.
What's the name of it? Softmax plus.
Like triangular.
Yeah, so mask.
And then so this is the mask, and then x square root of k. What does the x square root of k do? Like if we do something else?
That's the normalization factor, which you usually do. But like, what happens if you don't do that? I suppose it's going to be the same, but like
it's almost the same, yeah.
Yeah, I mean, I know that value doesn't really matter. Okay, I mean, this is kind of obvious. Like this just tells you that. So like if you compute this.
So okay, I think we need to get rid of the epilogue completely to understand a bit what's going on. Right. So
it just pays attention to that.
No, but what's still not clear to me is like why is there such a strong bias for a lower triangular matrix for like a Q and V that look almost random to my naked eye? Well, maybe they're not random, like right? Like we said that this has a strong bias for specific columns that are very red, and this.
Wait,
But
Wait,
this
wait,
is
I
YOLO.
remember.
This is everything.
No, I remember one thing. Like we see that it's gonna. So it has to be the same or different ones, right? Oh, I think I see. Wait. So I think first row of. I think those are not random. I remember seeing it somewhere that QK, they're
Wait,
gonna
wait,
be
wait.
like.
Check this out. Right. So you see here,
Yep.
we're basically we're taking an individual row of this and multiplying it by the entire K matrix, right? And the
But K
pattern
matrix
here,
is on top. K matrix is
yeah,
on top.
yes,
Yeah.
yes. And the pattern here looks very similar to the Q matrix, as in like we just have these like long rows that with very large values effectively has been the main thing. But like, why would this create this mask pattern, even though like we remove the epilogue, by the way, now?
Okay, can you go back to the visualization? Like here you can't see the Q, here you can't see key K, so like it's very hard to see anything. Like you just see the output. Like your K is on top or on the bottom? On the bottom. Yeah. So like in doing Q, which is a
Wait, you're right in that like it feels like it looks very similar to the like
I
it just
think on
looks like the K to me. Like it mostly looks
I
like a scaled
see.
K.
Yeah, okay, look at this. Look at this. This what's going downwards is like K.
Yes.
So if you look at it, you can see that like the right side of K is like so colors in the Q.
Mm-hmm.
If you look at them like on a single, let's say like the short dimension, the contracting one, okay?
Yeah.
If you take a look at short dimension Q, it stays the same for the whole hidden dimension. Like it's always red, green, red, green, red, green, whatever. You see?
Yeah.
And
I see what you mean. Yeah.
and in K, in the middle of it, it just becomes like kind of inverted. Like first on the left side of it, you go red, green, red, green, red, green, and on the right you go green, red, green, red, green, red. So that makes the triangular pattern.
So you're saying it has nothing to do with K, it's just primarily has to do with like the pattern in Q?
Well, the pattern in Q, this is again like the interleaving, which we were talking about. Like pattern in Q stays the same for the whole hidden dimension. Yeah? But
Pretty
pattern
much, yeah.
in K, pattern in
Yeah,
K is like
so you're right. Q almost looks like to me as if like you just have different columns that are like you just have red, then all blue, then all blah, etc.
yeah.
Maybe it makes more sense if I were to do it in a. Let's see if I do matrix vector, what happens? If I do matrix vector, okay, we get we're filling it up. The values all look the same. Does this help us build intuition? Let's see.
Yes, here it starts like changing, I guess, if you think of this.
Yeah, like it goes from mostly reds to mostly greens, basically, by doing this, right? And so,
Yeah. But like what you can check, that was a good view. This one, like check K from the other direction, like go 90 degrees to the left now.
90 degrees to the left.
So yes, exactly. You can see it here in the K. Like Q was like a single color row or like a column, whatever. You can
Yeah.
see K starts to change in like middle of it or like starts to change. That makes the triangular pattern. You see? Because if you check, for example, the which one is it? Okay, let me. Yeah, if you check the first, like the closest long dimension of K that we have right now, so it's like the first one. You see, the first
The
long.
closest long dimension of K. So this, it's mostly
Yes,
green. Yeah, sure.
but at the beginning of it, it's mostly red. It starts to change in the middle. You see, like if you zoom in.
Again, it alternates, right? Like it's not like this thing is half green, half red for me to.
Yeah.
Like remember when we were looking at this example, like the checkerboard pattern, like it was easier to sort of make this kind of argument where you could be like, oh, it's mostly green, therefore like it's going to be this. But here, like, it's like it does look like when I look at the Q and K, like that's not what I see. I don't see these sort of clean patterns. Like I just see. I mean,
Wait.
maybe the question we should be asking is like, if you're multiplying, because like, look, V looks mostly random though, right?
Yeah.
I think that we can agree with, right?
Yeah, we can't
Whereas,
leave anything from V.
yeah, whereas K is mostly like strong values. Basically, rows have similar values to each other, right?
No, I think the pattern that you should see in K is that like the colors start changing as you go in the hidden dimension.
The colors start changing as you go. You mean across the row, right?
Yeah.
Sorry, as you go across columns, the colors change, right?
Yeah.
So
I mean, there is a lot of like really strong ones. Actually, yeah, there is one. Like yeah, look at the bright green ones. You see, they start to get red at the end. Like
correct, yes. And then, but here, no. We look at this one.
yeah,
It's
I
like the
mean, I
same
guess
color
there's like
throughout.
no, but again, they start to get like smaller or less bright. I guess there have to be outliers, but I think this is what makes the pattern. Because like if you think of this, so let's say like the first, let's go like one by one basically. Show the attention mask and we can go by like one by one, you know? So like the 0, 0, the element on top left, you know,
Hmm?
that would be first row or column of Q. Okay, I think actually the patterns are dependent on each other. Like you can't just look at Q and see a pattern on it and see another pattern on K. I think they're just kind of dependent.
Yeah, that's my suspicion as well, by the way.
Yeah, that we're just trying to find a reasoning in something that there's none.
Let me check one thing. Give me a second.
Okay, I think I see how we should think of this.
I
Can
think,
you?
by the way, I think we're overcomplicating this. I think this is just like a property of the dot product. Like basically, um, like values that are close to each other will just be like similar indices will have high values, is basically what this comes down to. And that would
Yeah.
explain the strong diagonal, even with the completely random values. So let me see. I'm trying to vibe code like a NumPy program to just show this. Give me seconds.
I mean, the thing is, like, what you can see in those is like all of the Q and K, they are very like, it doesn't matter on the embedding. Like the embedding is the same in the whole dimension, I guess. So like the attention signal goes only from like a how can I say that? Like the attention signal. Let me actually get it more like straight.
Well, I guess, Mateo, there's also some questions in chat. Maybe they're relevant. You mind just taking a look?
Oh, wait, I don't see. Oh, I see. I was in the wrong chat the whole time.
Oh, you're in the private one?
Yeah. Okay, so the questions are like 1 hour ago, so I just sent a B and C as two linear layers. Okay, yeah, exactly. That's what I thought as well. I think that refers to the parallelism TCC. I think of VM prod as passing inputs token by token. Yeah, I think that's entirely correct. Like, yeah, like you're just doing vector matrix product every time you do not decode, prefill and generation when you do. Okay, at each step, the entire column is scaled by one value. That's the scaling. Okay. Yeah, I guess so. And yeah, split KHM, I suppose that speaks about the thing that I was talking about before, the how I was telling you, like how you can visualize it as or how you can think of it as a split K or like tiled matmul. I mean, the questions are like 1 hour old because I was in the wrong chat the whole time. If they're in the chat still, like next time, just ping me on Discord. That's a bit better, I guess.
Yeah, so at least like the this was kind of interesting. This is like a, let me share my screen again. This was a quick vibe code experiment. It's basically like trying to see if you just have completely random Q and K matrices, do you like recover like some strong diagonal, and you don't. Like basically this is learned and it has nothing to do with the
Yeah, but the thing is,
problem.
those matrices are hardly random. Like if you go and do like
Actually, yeah. What
the
about
matrices are
if
hardly random. Like they're very low rank is, I guess, the correct word. Like there's no value in the embedding dimension. You know, like the whole column or like the whole token is the same across the whole embedding dimension. That's the column-wise pattern that we observe. You know.
I mean, this was the original T-leaf assumption we had, which was that like if you have very strong rows or columns and you multiply those two matrices, you get anything interesting. Let's see what this vibe example says.
Wait, is that the thing? Oh, I see it. Go stream, because I forget, and then it's over.
Okay.
Okay, so first token in Q. That's the first row. You just do basically a cosine similarity with a first token in V or QK. Not you have it. I had the other way. So it's the bottom one. You just do a cosine similarity with K.
So red and blue will give you blue. Okay. Yeah.
No, you just
get blue.
similar values will give you big value. So what this tells you is that like the first row of Q is very similar to that one. Like first token in Q is very similar to like the rest of the tokens, I guess, or like has a strong signal together with the rest of the tokens.
And what do you mean by that? No, that's too high level. Like it's like you're saying it's similar. Like you're saying the row in Q is similar to the column in K, for example.
Yeah, they point to the same direction. Like if you think of them as a vector in high dimensional space, they point to the same direction. So like their cosine similarity is going to be large.
So the extreme example of this then is like if one is a transpose of the other, we should see diagonal matrix light up, right?
Yeah,
if
and that
A is
you
a
would.
transpose of B, I would expect.
Yeah, that's like A times A transpose. That's an identity matrix. I cooked so hard.
You did cook, yes. You did cook. You linear algebra.
I remember that cosine similarity exists. By the way, actually, like the first video that I saw on Attention talked about this, and I just randomly remembered that.
Oh, I see. Okay, let's try this.
It was like 7 years ago. I think it was from Yannick. I think it was from Yannick Kilcher. Or there was one more guy which had it. I don't remember. Yeah.
Okay, it's not. Well, actually, it is. Like all the values in the diagonal are pretty big.
Yeah,
so,
I think.
Yeah.
I mean, if you do like 8 times ATU, so like as you said, like the extreme case where you do like a transpose of one another, you're gonna get a diagonal. That's how linear algebra works.
So where do the so that's at the extreme, right? And then okay, I see. Okay, cool. I think I get it. So let's just do one last thing because I do have to head out soon.
I mean, 2 a.m. Do we want to actually understand V now?
No, we get it. We get it. Let me. There's something else. I want to see the This one, the parallelizing attention. Let's just do some distributed stuff.
Where is it?
So it says parallelizing attention. It's like section 5. So we visualize 4 of the 6 matmuls as a fused chain of matrices, confirming that the left associated chain is laminar among the shared y-axis. What does laminar mean?
I have zero idea. I don't understand English, but I think this is just parallelizing along hats. Yeah, it's gonna be parallelizing along hats. I think, yes. Can I open it?
Arranged in layers, I see, or flowing smoothly in parallel layers without turbulence.
Which one is it parallelized across?
Oh, I see. I think it's just like a fancy word for paralyzed. Like, but okay. To parallelize, we would partition the input into blocks along the y-axis. We can visualize this partition in the tool by specifying that a given axis be partitioned into a particular number of blocks.
Yeah,
okay,
that's
yeah, we do.
context parallel. That's context parallelism.
Okay, let's go. You said that to a few things already on the stream. Where you're like,
no,
this is context parallelism.
No. It was sequence parallelism, but that's the issue.
Like
some people call sequence parallelism, context parallelism, and so on. But yeah, this is context parallelism.
So this is context parallelism because we're only parallelizing the query.
Well, you would be parallelizing. I mean, again, it's not, I guess, but like this is how it would.
Yeah, so you would basically the K and V. I see. So basically, okay. The input is split over. Wait, just a sec. The input is split over multiple machines, right? And this is like this is a single batch, so it's not purely data parallel.
It's a single sequence. Think of this not as a batch, but a sequence.
It's a single sequence, right? It's just like, let's imagine that it's arranged in this 2D way, right? Then which means that the queue is also split over multiple machines, and every machine, like basically this would be like row-wise parallel over like multiple shards. You all reduce the queues such that you can then do the multiplication with K and then V, right? Why no?
Okay, let me actually think.
Because here, everything here can happen on an individual machine. Like there is no communication here so far. You just do it over an individual. Like you get a slice of the input, and every shard has the entire WQ.
Oh yeah.
Right.
Correct. So like, if you think of attention, like the only part that like depends on the whole previous, like you need that's also how KV cache works. Like you can just cache the previous K and V, but you need the full queue. So in this case, like you do queue with the full KV. That's like the first row of attention. Then you do second queue, which is another 32 tokens, and you check like how many of those, like where do those 32 tokens attend to. You don't need to do any communication at all with that. Then you do third batch or like third 32 tokens, and so on and so forth. So you don't need to do any communication in this case. Your attention mask is just going to be sharded across the like the first dimension, I guess. That you can't say.
So okay, I see what you mean. You're not all reducing, but you're sending to every shard the full K and V matrices.
Yes.
They are then each computing a chunk of attention, and then you all reduce that to you all gather that, and then you get the full attention matrix. Oh no, you're still not all gathering actually.
Yeah, you don't need to.
Yeah.
You can do the all gather at the end, like when you have the
out. I see. So this is context or sequence parallelism, by the way?
This is neither, actually. But it's very close to like ring attention and context parallelism. Because in the ring attention or like context parallelism, as we usually do that, for example, how Torch does it, is you would also have K and V split by sequence dimension. I don't think you're gonna find that here. Yeah, you're not. Oh wait, is this it? Wait, is this it? No, it's not. Okay, I can talk about this one quite well, I think so. It's very simple. You really don't have to do this. Can you get the image before? That one was way better, or what I was gonna show. No, the original one that we were like, you were asking me if it's a context parallel or not.
Oh, I moved on mentally, but
Yeah.
let me pull it back. Oh, he's doing more parallelism here.
Is he? Wait. Oh yeah, this is context parallelism, I think. No, wait. Yes, yes, it is.
Double partitioning. We visualize sum which invocates the block parallel pair transformer. What is this?
Or it's not.
This is the guy who came up with ring attention, I think.
Yeah, I
It's
think this is just ring
yeah.
attention, actually, like.
It's the same. I think it's the same author.
Yeah. So how ring attention works, I can actually.
Yeah, this is him.
Yeah. Yeah. Okay. So we can actually showcase ring attention on this very easily. So you see that. I mean, it kind of. You can see that like Q, K, and V are both sharded across a V dimension, across a sequence dimension, right?
Yeah, they're the column, sure. No, row.
So
they're sharded across their rows, yes.
across
No,
the sequence dimension.
No, it depends
Sequence.
actually.
No, it's all sequence dimension.
It
is.
Sequence dimension. It is, yes, you are correct. Yes. Okay.
Yeah, so attention, like you would need. So in attention, the problem is the softmax. You're doing row-wise softmax in the look at the attention. You would do row-wise softmax. So you need a 4-row to get something that you can do a softmax over. So how you do that is like you have your own Q shard, which you just have. You just chill with that one. Like your GPU 0, you chill with Q shard 0. And then comes the nice thing called ring attention. So the other GPUs just start sending you in a ring pattern, just sending you their shards of K and V. So like you do Q0 times K0, that's gonna be like your first block. Then you do Q0 times K1, which you got from the another GPU.
So the fine sending you mean rank 0, or you mean all GPUs sent to their neighbors?
Sent to their neighbors. Like you just go in a ring. That's why it's called ring attention. So like you start passing around the K and V shards around, and compute like the small blocks. Meanwhile, you can do online softmax on that. So like it's easy, and then you just compute with V, and you're doing fine. Because
I see. Wait. So sorry. So like here, the right way to split this would be, let's say each machine has a different shard of Q.
And K and V.
Wait, no. Let's say it just has. Let's say it owns. Let me just finish the point. So it just has Q, and then it's like, okay, great. Like this means I can compute I am responsible for computing this first block of columns in the attention matrix.
First row, but correct.
First block, first column. No, it's like boom, boom, column.
Is it so?
Which means that yeah. So then you're like, okay, great. I have the Q,
it's for sure row.
Hey, let me finish.
It's for sure row, but that's just the only thing. Like it's for sure row, but the context is gonna stay the same. It has to be row because like.
Oh. Oh, I see. Yeah, yeah, because you're scanning like the. So yeah, you're still projecting over the sequence dimension.
No,
So you're project
across hidden. You're
the hidden
contracting over
dimension.
sequence. Yeah, sequence.
Contracting
Okay,
over
correct. Yes,
sequence. Yeah.
yes, yeah,
Okay. So basically, then for every new like basically block of attention you need to compute, like the shard that owns like the queues don't move around. And then you're
yeah,
like, okay, what's the K and V that I'm missing to compute the next batch? And then you figure out like the right strategy to overlap this and blah blah blah. Okay.
yeah. The right
Okay.
strategy is ring.
Yeah.
Ring. If you're then like with causal masking, it becomes a bit more difficult because like imagine like with causal masking, like the first queue just needs to compute very few. Like it just needs to compute the first block. Imagine that. So, and the last one needs to compute actually the full row. You see what I mean?
Yeah, I do.
Yeah, so that's why with causal masking, you do round robin strategy, where you just go like the other way around, like, just to like. Okay, I can't like explain round robin without going, but like it's basically gonna do load balancing better for this, So like the first GPU is computing like.
All right, Matej, I think I get it, and I think I'm satisfied with concluding here. So I might go grab a bite, and maybe I'll be online later. But you
Yeah,
should
it's
go get some.
2:20 a.m. again. Like I'm.
You still have another 4 hours of hanging out. It's like,
Oh yeah, I went to bed at 6, so I might as well work a bit. Yeah, but
all
I
right,
think I'm satisfied as well with like.
sounds good. Well, thank you,
Yeah,
TCC, for hanging out for so long as well with us, and we'll see everyone soon. Thank you.
yeah. See you.